Welcome to a non-homogeneous heat conduction example. So in this example, a 40 centimeter rod has one end fixed at 5 degrees Celsius and the other end fixed at 25 degrees Celsius. Let X be the position along the rod measured in centimeters from the 5-degree end. The initial temperature along the rod is given by f of x equals 10. An external heat source transfers heat to the rod at position X at a constant rate of h of x equals 5. Our job is to find the formula for the temperature at position X and time t. So in this case, our L is 40. One end fixed at 5 degrees. The other end fixed at 25 degrees. We have U of 0t is equal to 5, and U of LT, or U of 40t, is equal to 25. So again, this 5 is what we previously were calling our U naught. 25 is what we previously called UL. We have U of x0 is equal to f of x, which is 10. So this is our 10 is our f of x. And then we have external heat source, h of x equals 5. So we have u, first partial with respect to t of u is equal to the second partial with respect to x of u plus h of x, or plus 5. Our job is to find the formula for the temperature at position X and time t. So again, recall that we have U of xt is written as V of xt plus Q of x, and Q, where Q is a solution. To a squared q double prime equals negative h of x, with q of 0 equaling u naught and q of L equaling u sub L. So we are looking at here. Oh, I forgot to say what a squared is. Let's say find the formula for temperature at position X and time t if A is equal to 5. And I forgot my a squared in my equation here. We should have u sub t is equal to a squared uxx plus 5, and our a squared would be 5 squared. All right, there we go. So we have then that we are looking at 5 squared times q double prime is equal to our h of x was 5, so is equal to negative 5. Our q of 0 should be equal to u naught, and u naught is also 5. I have a lot of 5s in this problem. Our q of L is now q of 40, and that was equal to 25. So we are looking at q double prime is equal to negative 1/5 That means that, oops, that means that Q prime should be equal to negative 1/5 T plus C1. Now we have Q should be equal to negative 1/10 T squared plus C1 T plus C2. Q of 0 equaling 5 implies that our C2 has to equal 5. So we have Q of X. I apologize, these should be X's, not T's. Q is a function of X. We have negative 1/5 X plus C1 and then negative 1/10 X squared plus C1X plus C2. We have Q of X is equal to negative 1/10 X squared plus C1X plus 5. We also know that Q of 40 is equal to 25, should be equal to negative 1/10 times 40 squared plus C1 times 40 plus 5. So we have 25 is equal to negative 160 plus 40 times C1 plus 5. That becomes negative, sorry, that would be moving over the 5, we would have 20, and then adding 160, we have 180 is equal to 40 C1, or C1 is equal to 18 divided by 4, or 9/2. So we have our Q of X is negative 1/10 X squared plus 9/2 X plus 5. Then we have, and we have that V of X, T, satisfies, or is, V of X T equals the sum from n equals 1 to infinity, C sub n times e to the negative a n pi over L whole thing squared T times sine n pi over L x, with Cn equaling 2 over L times the definite interval from 0 to L of f of x minus q of x times sine of n pi over L x dx. So plugging in, we have v of xt is equal to the sum from n equals 1 to infinity of c sub n times e to the negative 5n pi over 40 whole thing squared t times sine of n pi over 40 x, and c sub n is 2 over 40 times the definite interval from 0 to 40 of our f of x was 10. We'll have 10 minus our q of x. Q of x was negative 1/10 x squared plus 9/2 x plus 5. And this whole thing is multiplying sine of n pi over 40x dx. If we now solve for Cn, we get Cn is equal to 1 over 20 times the definite interval from 0 to 40 of, this would be 1/10 x squared minus 9/2 x plus 5. 10 minus 5 is 5, all times sine of n pi over 40x dx. Up to you if you want to split this into multiple integrals and do multiple levels of integration by parts, or we can just do one massive integration by parts. If we do one massive integration by parts, our u would be 1/10 x squared minus 9/2 x plus 5. Our dv is sine of n pi over 40x. Differentiating on the left side, we would go to 1/5 x minus 9/2, then to 1/5, and finally to 0. Integrating on the right, we would go to a negative 40 over n pi times cosine n pi over 40x, then a negative 40 over n pi entire fraction squared sine of n pi over 40x. And then we would go to a positive 40 over n pi entire fraction cubed cosine n pi over 40x. We do the positive product on the first diagonal, negative product on the second diagonal, positive product on the last diagonal. We are looking at our c sub n's are equal to 1 over 20 times, we have our negative 40 over n pi times 1/10 x squared minus 9/2 x plus 5, all multiplying cosine n pi over 40 x. Then we are adding on 40 over n pi squared times 1/5 x minus 9/2 times sine of n pi over 40x. And then we are adding on a 1/5 times 40 over n pi entire fraction cubed times cosine n pi over 40x. And we are evaluating this from at 0 and 40. Plugging in 40, we have 1/20 times negative 40 over n pi times a 1/10 40 squared minus 9/2 of 40 plus 5, all times cosine of n pi. Then we have a plus 40 over n pi, entire thing squared, times a 1/5 times 40 minus 9/2, all multiplying sine of n pi. Then we have a plus 1/5 times 40 over n pi, entire thing cubed, times cosine of n pi. This was just a plugging in 40 term. Then we will subtract off. We would have a negative 40 over n pi. If we plug in 0 to our quadratic, 1/10 x squared minus 9/2 x plus 5, we just get 5 times cosine of 0. Then we have a plus 40 over n pi squared times, if we plug in 0 to 1/5 x minus 9/2, we wind up with a negative 9/2. And then that is times sine of 0. And then we also have a plus 1/5 times 40 over n pi, whole thing cubed, times cosine of 0. And all of these pieces were being subtracted off. This entire 6-line setup is being multiplied by that 1/20th out front. So going through, cosine of n pi is -1 to the n. Sine of n pi is 0. Cosine of n pi is again -1 raised to the n. Cosine of 0 is 1. Sine of 0 is 0. And cosine of 0 is 1. So our second row and fifth row entirely cancel out here. That 1/10 40 squared, we are looking at 160. That minus 9/2 of 40 would be minus 180, would be -20. Plus 5 is -15. So we have our Cn is equal to 1/20 times -40 over n pi times -15 and then the next line went to 0, so we'd have plus 0 and then plus 1/5 plus a -1 to the nth times 1/5 times 40 over n pi, whole thing cubed. And we are subtracting off a -40 over n pi times 5. So this becomes plus 40 over n pi times 5. And then we're subtracting off a positive 1/5 times 40 over n pi cubed. So we are subtracting off, oh, then we have a -0 and a minus then 1/5 40 over n pi, whole thing cubed. This becomes 1/20 times, we have -40 over n pi times 15 plus a 40 over n pi times 5. So that's 40 over n pi times 20 in total, would be 800 over n pi. And then we have a plus -1 to the n minus 1. That all multiplying 1/5 times 40 over n pi, whole thing cubed. If we multiplied in our 1/20, we are looking at a 40 over n pi plus if we do our 40 cubed divided by 20 divided by 5, we wind up with 640 over n cubed pi cubed times -1 to the n minus 1. I'm going to leave this in this format. Note that this will be 0 in the case that n is even, or sorry, it won't be 0. The 640 over n cubed pi cubed term would go to 0 in the case that n is even, and it would go to -2 times that in the case n is odd. But we'll just leave it in this format. And so what we get then is that we have u of xt is equal to we have, I'm going to put our Q of X out front actually. So our Q of X was negative 1/10 X squared plus 9/2 X plus 5. So we have negative 1/10 X squared plus 9/2 X plus 5. And then we have plus the sum from n equals 1 to infinity of 40 over n pi plus 640 over n cubed pi cubed times negative 1 to the nth minus 1 times e to the negative a n pi, so 5n pi over L over 40, all things squared t, times sine of n pi over 40x. So this is our non-homogeneous heat conduction problem. It's a little more work, just in that we have to solve for that Q of X first. But once we have Q of X, it's equivalent to solving a homogeneous problem. We just have to change our f of x to f of x minus q of x. Otherwise, it's just like our standard homogeneous problem for the series component. So again, this is how we go about solving a non-homogeneous heat conduction in a rod problem.